Okay, so you just kind of gave a business pitch for your revolutionary new business. Yeah, a food service company where they take a bite out of the food you eat. Well, anyway, your pitch didn't go so well, and so you decided to get drunk. And now that you're finished getting drunk, you have to go take the train back home because this is in Europe where they actually have trains. On the train, you're drunk and you decide to just start playing with your laser pointer and just pointing it wherever you want. And you try pointing it at the ceiling, which is metal, and the light reflects back right into your eye and permanently blinds you, and you have to go to the hospital. The thing is that after your horribly failed business pitch, you're feeling very insecure and self-conscious, and so immediately the first thing you wonder is, what would it look like from someone outside the train if they were to see you blinding yourself? What you realize is that, to you just saw laser light go up, hit the ceiling, and then go and blind you. But from the perspective of someone outside the train, the laser light getting emitted and you getting blinded happened at different points in space because the train moved. So the actual path of the light looks something like that to them. And we're working in like one uniform space, right? Space stayed the same. Obviously, the speed of light stayed the same, since that's the whole premise of all of this. The only thing left to change, given that speed is distance divided by time, is time. And so we say that time out in this outer case, basically time is traveling slower, and this is time dilation. So the extra distance is accounted for by more longer difference in time. And if you go through the geometry of this, you find that the change in time outside of the train, which depends on how fast the train is going, that's because it's some number, which this is called gamma. It depends on how fast the train is going. That's defined like this, but that doesn't really matter. The important part is just that it depends on how fast we're going. Times what's called the proper time, which is the shortest possible time. It's the time when you're following the action. And in this case, that's inside the train. And so this tells you time dilation. So normally we like to think of stuff happening at like a point in space. And if we have some sort of change of our frame of reference, so maybe we're like looking at it from a rotated perspective or something, there's some transformation, which I'll just call A, that transforms those coordinates such that we get new coordinates, in the new space, something like that. But under relativity, we know that this transformation, if it involves anything anywhere going close to the speed of light, that actually changes time as well. And so in order to account for that, we have to add a new dimension to our coordinates, which is time. Boop. The sort of annoying thing here, though, is that these are all in different units, which, just kind of seems weird. It also messes with a bunch of stuff that happens later on. So what we do is we multiply this by the speed of light, and now everything is in units of length. And we're all happy, and this is what we call our position in space-time, and we usually call it capital S. Anytime you see a capital letter, it's probably one of these four-dimensional space-time vectors. The problem here is we don't really have a good analog of distance in space-time, yet at least. So normally the way we define distance is, distance squared is equal to x squared plus y squared plus z squared. But, of course, that doesn't work here because we have this extra time component. How do we deal with that? And under relativity, if we just ignore the time component, that doesn't work. Distances are not agreed upon in every frame of reference. We need something that's the same in every frame of reference. And it turns out how we get that is what's called the relativistic invariant, which we denote with S. And it's very similar. I'll just write it without the deltas. T squared minus x squared minus y squared minus z squared. And there you go. It's literally the same thing, except everything except time is negative. The reason is because this does not exist in a normal sort of space. This exists in what's called Minkowski space, but that makes it sound difficult and technical. So I'm going to call it a Wazowski space. Now, the reason Wazowski spaces are special is because they have a different definition than normal of what an operation that's very important that we call the inner product. And the inner product is written like this, where we have two vectors, A and B, and these are vectors. And in normal sort of algebra, it's the sum over all possible i's of ai times bi. So it's just you go one component at a time. So if I have 1, 2, inner product 3, 4, it would be 1 times 3 plus 2 times 4. And this would go on for however many components you have. In Wazowski spaces, it's defined using something called the Wazowski metric tensor, but we don't need to bother with that. All that matters is that if we have two vectors A and B in Minkowski space, their inner product is going to be something like, where these are four-dimensional, it'll be something like A plus A1 plus B1 minus A2 plus B2 minus A3 plus B3 minus A4 plus B4. Right, so just like with our definition of distance before, the first time component is, we keep that positive and everything else becomes negative. And that's all there is to it. But anyway, now that we have our fancy pants Minkowski space, version of position, we can also try and get a version of velocity. Now, I have to be careful here. We can't use normal time. And the reason we can't use normal time is because that's not the same in every reference frame. So if we were to try and do something like this, that wouldn't work because, like, what is t? That's different in different reference frames. What we can do is use the proper time, tau, which is the shortest possible time. It's usually the one where you sort of follow the action, if you remember from the beginning. And that gives us this. What's interesting here is that we can expand this. So we call this the 4 velocity u, because it's just velocity with 4 dimensions. And if we were to write out the components, we have d over d tau. C is a constant we can split out, dt d tau. And then we have dx d tau, dy d tau, and dz d tau. Now the important thing here is, remember, if you remember what we got from time dilation, which was that delta t equals this weird number called gamma, which is based on the velocity, times delta tau, then that tells us that dt d tau, if you just take the derivative, is equal to gamma. And that also helps us solve those cases here, because we can actually break up this dx d tau, we can break it up as dx dt times dt d tau, which gives us gamma times the normal, boring, classical velocity in the x direction, which I'll write vx. So that's great. We can now write our 4 velocity, our special Minkowski 4 velocity, as c gamma, gamma vx, gamma vy, gamma vz. And before we go any further, there's one sort of little tiny detail, which is that the inner product of any 4 velocity with itself is equal to the speed of light squared. You can go through the math of this if you want. I'm not going to bother. Satisfied with everything you've done so far, you realize that the only thing cooler than time dilation and all this wacky stuff is becoming a Jedi. So you decide to go play the MMO Star Wars The Old Republic and look at all the different Jedi skills, and you discover that there is a tier 1 defense Jedi Guardian skill called momentum. So you do some Googling and discover that momentum is mass times velocity. And we just found velocity, so let's try multiplying it by mass. The amount of matter in an object, not like going to church. So if we take relativistic, 4-dimensional momentum to be mass times relativistic 4-dimensional velocity, which makes sense enough, and we expand it to all of the components, we get c m gamma, gamma m vx, gamma m vy, gamma m vz. And we don't really know what this stuff is here. We're just going to call it, well, I don't even know what it is. It doesn't matter. We'll just call it, we'll just break our vector off into a little bit, and we'll call this little bottom part lowercase p. Lowercase p is going to represent whatever this thing is. It doesn't really matter. It's part of momentum, but it's fine. We're fine. And then we have the cm gamma thing, which is just sort of weird. Like, what even is cm gamma? And the solution to this comes from what happens if you expand mc squared gamma as a Taylor series, which sounds fancy, but what happens is, it turns out you can just rewrite this as mc squared plus 1/2 mv squared. Remember, v, gamma contains v, that's what it's based on, plus a bunch of other terms that only matter if you're going really close to the speed of light. And we know what this is. This is ordinary kinetic energy. I don't know if that exists in the Star Wars game, but at least in high school physics it did. And so this whole thing must be an energy term. And it turns out that, yes, this is what we'd expect. This is kinetic energy. This is a bunch of corrections that make kinetic energy work for relativistic velocities. And this is the famous E equals mc squared, the sort of internal energy that all matter has. And what this means is that if we take E divided by C, that will give us mc squared gamma divided by c, which is just mc gamma. And so that weird first term of momentum turns out to be proportional to energy. It's energy over c. And then we still have that weird p thing there, which we don't really know what it is. But that's okay, never fear. It turns out that we can get that another way. So remember when I said, whoops, the inner product of any 4 velocity with itself is c squared? What about the inner product of any 4 momentum with itself? This turns out to be a very useful number that doesn't have its own name, even though it kind of should. Well, this is just, we can factor out the masses, right? Because p equals mu. There's masses in both of these cases, so we have mass squared times that, which is equal to mass squared c squared. And this is very important. This is great. We have a definition of momentum inner producted with itself. And it's just mc squared. We can do better than this though, because there's another way for us to find the inner product, which is to actually find it the way we normally do. Before we were using that fun little trick. Now we can actually just write it out. So we have the first term of momentum, which is, we remember, is E over C. So we have E over C squared minus all of the other bits. So in this case, that's just going to be P squared. Because remember, we broke this down as E over C is our first part, and all the other 3 components we just decided to call little p. Now, this is cool and all, but what we can do now is rearrange this a little bit. We can say mc squared equals E over C squared minus P squared. We can multiply everything by C squared. So we get mc squared equals E squared minus PC squared, and rearrange it a little bit to get E squared equals mc squared plus PC squared. And this is a very famous equation called Einstein's energy momentum relation. And it's just great. It's just great. And in our case, it lets us finally figure out what this dang P is. Like, what the heck is that? Now, in this case, we want to know what happens with a massless particle. So what we're going to do is set the mass to 0, which makes all this stuff go away. And then we just get E equals PC, or P equals E over C. Oh my gosh, we did it. We found what this weird thing is. And that tells us that we start with E over C. And then this is all in terms of magnitudes, right? So whatever this P is, the magnitude of P, if we were to write it as vector, is E over C. Or another way to phrase that is, if we call the direction the photon is traveling, we call that n with little hat because it's a unit vector. Then what happens, what we can do is we know that the vector P, little p, is equal to E over C times that vector, because the momentum and the velocity are always in the same direction, and we know this is the direction that the photon is traveling in. And that's all we need to finally describe the momentum of a photon. It's the relativistic 4 momentum, so it's a 4-dimensional quantity that goes E over C, and then all the other remaining 3 dimensions are E over C times just in whatever direction it's going. Now, there's one last thing, which is, like, are we sure photons have energy? And the answer is yes. It comes from quantum mechanics. If you're really curious, energy is equal to H is the Planck, just a constant called Planck's constant, times, this is Greek letter nu, which is the frequency of the photon. And so E over C is equal to H divided by the wavelength of the photon. There's a bajillion ways in which light having momentum turns out to be super important for physics, but probably the coolest example is what are called solar sails, where you just put a huge membrane out in space where there's no friction or anything like that to worry about, based generally speaking. And the light from the sun, all those photons hitting your solar sail will actually push it, and you get propulsion that way.